listeners and viewers. Welcome to Kaduna State Ministry of Education Radio and TV e-learning program designed for our SS3 and other students staying at home due to the coronavirus pandemic. The present administration, under the able leadership of His Excellency, Malam Nasir Ahmed El-Rufai, is positioned, as always, to ensure that under his leadership, our students are not left behind in all areas of human endeavors, especially education. Kaduna State is the center of learning. Therefore, we want to ensure that our students excel in their forthcoming examinations and beyond. Students and other learners at home are given this opportunity in order to continue learning, as education is a continuous process. Different subjects will be taught in this program to assist students to perform excellently in the forthcoming Senior School Certificate examination being conducted by NECO and WAEC as soon as schools reopen. Teachers making presentations will always provide their names and phone numbers during each presentation, and they can be contacted for questions, further explanations, and/or clarifications. The following numbers and contacts can also be reached for expression of any concern or observation: 090-865-00545 or 080-383-62072. Our website is www.education.kdsg.gov.ng. Our email education@kdsg.gov.ng or education.kdsg@gmail.com. Our YouTube channel, Ministry of Education, Kaduna State. Our Twitter handle @Kaduna_MOE. Or our Facebook page, Ministry of Education, Kaduna State. Stay safe, stay at home, and learn well. Thank you, happy listening, and happy viewing.
Hello learners, good day. Welcome for another session of e-learning. We are looking at the subject physics again, and the topic is energy quantization. And under it we have atomic energy levels. What is energy quantization? It's simply the process by which a packet or radiation of energy known as photon or quantum, and its plural as quanta, is emitted when heat is applied or when the temperature of a substance is high. That's just what it implies. That is, bits of energy, instead of a continuous form, it is broken into piece by piece. And then energy levels, also called electron shells, are fixed distances from the nucleus of an atom where electrons may be found. That is, distances that are fixed from a given nucleus in an atom are referred to as energy levels. Now, in 1902, Max Planck postulated a theory, and is of radiation or quantum hypothesis, which suggested that substances emit or give out radiation energy, and it happens in separate amount or discrete fixed amount. And those fixed amount are known as energy quanta. And the value for that energy is always given as HF. As you can see here, the F there stands for frequency or radiation, and H is Planck's constant. The energy of radiation, therefore, can be given as E equals to NHF, where N there is integral values of 1, 2, 3 up to infinity. That is, capital E is equal to HF or 2HF or 3HF up to a value E naught, and is equal to 0. Electrons in atoms occupy energy levels or electron orbits or shells around nuclei, singular nucleus. Energy states or levels are numbered, as I said, from 1 to infinity. Electrons in the orbit closest to the nucleus have the highest energy than those in higher levels. The closest orbit to the nucleus is called the ground state or lowest energy level, and the quantum number given is 1, with corresponding energy level E naught, as stated before now. Then other energy states or levels are called excited states, with N equals to 2, 3, 4 up to infinity, and the corresponding energy levels as E1, E2, E3, and E infinity. Energy of an electron is given by E equals to minus 1 all over n square E naught, where our n is our electron's quantum number or principal quantum number, and our E naught is ground state energy. The minus sign there signifies that one must do work on that electron to be able to remove the electron from the atom. That is, our capital E there stands for the energy of a given level. The E naught is the energy of the ground state, and n is our principal quantum number. Now, we know that in an atom, we have electrons reside on orbits, and the nature of the orbits are circular. But because of explanation, we represent those orbits as horizontal instead of circular form. And so horizontal lines are drawn to represent energy levels as shown below for a case of hydrogen. And such are called energy level diagrams. Such a diagram is called energy level diagram. The diagram is as you can see here. In the diagram, the title is energy levels in the atom. It is not to scale. When n is equal to 1 on my right hand side here, the corresponding energy is E naught. This is what we have as a formula we can use to write the values of energy for principal quantum number corresponding. When n is 2, and it will be E2 minus 1, giving you E1. And when n is 3, it will be E3 minus 1, give you E2, and in that order. And as you proceed upward, the increase of the energy, values negatively happens or take place. When it keeps on going, even though you have what we have there, the spacing of the lines are not the same. They are not the same as you proceed. And by the time you have up to n equal to infinity, ionization takes place. And you can see a spectrum there showing you a continuous spectrum. The E epsilon, the E infinity is equal to 0. That is, at that point is equal to 0. Then we have our ground state atom must be stable. That is, at the ground state, the atom is always stable. When the electron is infinitely far from the atom, that is, it is completely removed from the atom is said to be ionized. So, ionization is simply referred to removal of an electron from an atom. The nature of this state with n equal to infinity, as shown in the diagram above, is defined as 0. That is, E infinity is equal to 0. The 0 value shows that the valence, that is the outermost electron, is always free from attractive force of the nucleus by proton. At this point, an atom accepts continuous as well as discrete fixed amount of energy. That is, it cannot only accept fixed amount of energy, but even continuous one. And then what is ionization energy? It's a ground state energy. It is the energy required to remove an electron completely from an atom. Energy of an atom is always constant. But when an atom absorbs energy enough, it raises the energy of that atom, and it is referred to as excitation. There is no intermediate energy changes that take place between the atomic energy levels. An atom always exists in one of a set of well-defined energy levels, and physical systems always have a tendency of remaining in the lowest energy or ground state. Excitation is simply a process of increasing the energy of an atom, either by heating or bombarding that atom with an energetic particle. The excited energy is always referred to as minimum amount of energy required or needed to raise an atom from the lower state to higher energy state. When excitation takes place, one or more of the electrons absorb energy and therefore move from a higher level, move from a lower level to a higher level or an excited state. And because of these excited states are not stable, when electrons is not in its own orbit or state, you discover that it tends to be unstable, and so it quickly jumps back to its original lower level, and it emits a photon or quantum of energy with a characteristic frequency f or wavelength lambda in the process. And according to the relation delta E, that is change in energy, is equal to E subscript n minus E subscript naught, equals as equation 1. And equation 2 is change in energy delta E equals to HF subscript n, and equation 2. As then we can replace our HF by C over lambda n. And with that, delta E is equal to AC over lambda n, lambda subscript n, given on equation 1. What is 3? Our delta E, we said, is equal to E naught minus En minus E naught as equation 1. That is change in energy. When an electron jumps from either a higher to a lower energy level, we call it change in energy, and is referred to as excitation energy. And what we have is the energy at the higher level minus energy, for instance, at the ground state. It is not restricted to ground state. It can be energy at the higher level to energy at any of the other lower levels, and that level could be excited state. It can be any of the levels. Now our equation 2, we replace our equation 1 with this hf subscript n as h Planck's constant frequency for f, and then our delta E remains change in energy. We can also refer to it as delta E is equal to AC over lambda n, equation 3. Our delta E is equal to change in energy, and as I said, is referred to as excitation energy, where En is energy in the excited state. Our N is equal to 234 as I explained before, and then the ground state energy is our E naught with N equals to 1. As I said, the En minus a given energy lower is from higher to lower. So whether an electron absorbs or emits energy, change always occurs in the energy, and the energy always is equal to energy at higher level minus energy at lower level. That's just the implication as equation 1 depicts, even though we are using ground state for the lower, but any other lower excited state or energy level could be used, while En refers to the higher energy level. And that is, it implies from what we have just said that energy loss is equal to energy emitted by a photon and by an atom, or energy gain is equal to energy absorbed, by absorbed photon. Energy loss or gain by an atom is equal to energy of emitted or absorbed photon. That's just what it implies. And this, therefore, could be shown in the diagram below. The diagram here shows that if you have ground state E naught, and our E1 for the first excited state, E2 is the second excited state, E3 is the third excited state, and E4 the fourth excited state, we have the change in energy. The first line diagram that we have there is delta E equal to E3 minus E naught, giving us that the change is from this third excited state or the fourth energy level to the ground state. And then for the second case, you have change in energy is equal to E2 minus E naught. That is, the electron jump from the second excited state, that is E2, or the third energy level. Please don't get confused. Our E naught is our first energy level, E1 is our second energy level, E2 is our third energy level, and in that manner. But when we talk of this E1, E2 is referring to the excited state. After the ground state, any other level is referred to as excited state. So our second case there have delta E is equal to E2 minus E naught. Then our delta E there is equal to E4 minus E1, as you can see, and then delta E is equal to E4 minus E naught. This is what we refer to as energy transitions. Examples are given. An electron jumps from one energy level to another in an atom, radiating 4.5 times 10 to the power minus 19 joules. If H is equal to 6.6 times 10 to the power minus 34 joules second, and C equal to 3 times 10 to the power 8 meter per second, what is the wavelength of the radiation? Solution. Delta E is equal to En minus Em. Delta E is equal to Hf. Delta E is equal to Hc over lambda. Making lambda the subject from this third equation, lambda will be equal to Ac over lambda and delta E, where the delta E is the change in energy. And the substitution will now give us lambda is equal to 6.6. That's for Planck's constant times 10 to the power minus 34. Speed of light C is 3 times 10 to the power 8 over delta E, change in energy, 4.5 times 10 to the power minus 19. By the time you compute your values, lambda will now be equal to 4.4 times 10 to the power minus 7 meter. Example 2, an atom excited to an energy level E2, open bracket, equals to minus 2.242 times 10 to the power minus 19 joules. It falls to the ground state E naught and is equal to minus 21.8 times 10 to the power minus 19 joules. Calculate the frequency and the wavelength of the emitted photon. Given Planck's constant, as you can see, our delta E therefore is E2 minus E naught, giving you Hf. E2 therefore minus E naught is equal to Hf, making F the subject. It becomes F is equal to E2 minus E naught over H. Our E2 is a minus 2.42 times 10 to the power minus 19. minus ground state minus 21.8 times 10 to the power minus 19. By the time you open bracket, you will have F equals to minus 2.42 times 10 to the power minus 19 plus 21.8 times 10 to the power minus 19, all divided by our Planck's constant, 6.6 times 10 to the power minus 34, 6.6 times 10 to the power 34. F now therefore is 19.38 times 10 to the power minus 19 over 6.6 times 10 to the power minus 34. Our frequency now gives us 2.94 times 10 to the power 15 Hz. C, which is our speed of light, is equal to F lambda, and lambda now is C over F. Lambda is equal to 3 times 10 to the power 8 over 2.94 times 10 to the power 15. Lambda is equal to 1.02 times 10 to the power minus 17 M. Example 3. If the ground state level of the hydrogen atom is minus 13.6 electron volt and the excitation energy of the electron is 12.09 electron volt, find the energy at the excited state. Solution is delta E is equal to En minus E naught. Substitution gives us 12.09 equals to En minus bracket minus 13.6. 12.09 equals to En plus 13.6. En is made a subject to give you 12.09 minus 13.6. En is equal to minus 1.51 electron volt. And then B is equal to En is equal to E naught over N square minus 1 by substitution you have minus 1.51 equal to minus 13.6 over N square. N square is equal to minus 13.6 over minus 1.51. Our N square is 9.006. N is equal to square root of that value, give us 3.001. N is equal to 3. It means it is a third energy level. Excited state is energy level minus 1, and that will be N minus 1. 3 minus 1 give us excited state 2. That is second excited state. And then D, delta E is equal to HF. F is equal to delta E over H. The values of HF of delta E is 12.0 times 9 times 1.6 times 10 to the power minus 19 over 6.63 times 10 to the power minus 34. Frequency is 2.92 times 10 to the power 15 Hz. C is equal to F lambda. Lambda is equal to C over F. Lambda is 3 times 10 to the power 8 over 2.92 times 10 to the power 15. Lambda is 1.03 times 10 to the power minus 7 meter. With this given to you as example, we are expected to solve more of it over and over, and you have no problem. I call on my colleague to come and summarize the work and give you work that will keep you busy and you make other consultation. Once again, I remain Napoleon Kure.
Good day, learners. I'm here to give you an assignment to do while you stay at home on what my colleague has already delivered to you. Question 1. A photon of wavelength lambda naught is emitted when an electron in an atom makes a transition from a level of energy 2E subscript k to that of EK. If the electron transits from 4 over 3E subscript k to EK level, determine the wavelength of the photon that will be emitted. Question 2. An electron makes a transition from minus 3.4 electron volts energy level to minus 13.6 electron volt energy level. Calculate the A, energy lost, B, frequency of emitted radiation, C, wavelength of emitted radiation, given that 1 electron volt is equal to 1.6 times 10 raised to power minus 19 joules. H, Planck constant, is equal to 6.6 times 10 raised to power minus 34 joules second. Question 3. The hydrogen atom has an ionization potential of minus 13.6 electron volt. Calculate the energies of the ground state and the first two excited states. Use these energies to draw an energy level diagram and indicate on it all the transitions possible when the two excited states de-excite. Calculate the frequencies and wavelengths of these transitions. 4. If the energy for the ground state of an atom is minus 24.8 electron volt, find the A, energies for the third and seventh states. B, excitation energy between the states n equals 1 and n equals 5. C, frequency and wavelength of the photon, given that 1 electron volt is equal to 1.6 times 10 raised to power minus 19 joules. Planck constant small h is equal to 6.63 times 10 raised to power minus 34 joules second. And small c, speed of light, is equal to 3 times 10 to power 8 meters per second. And finally, question 5. In a model of the hydrogen atom, the energy levels Wn are given by the formula Wn is equal to minus E naught all over n squared, where n is an integer and E naught is a constant. Determine the energy released in the transition from n equals 3 to n equals 2. References: 1. New School Physics by M.W. Anyakoha. 2. All-Inclusive Calculations in Physics by Solomon Dauda Yako. 3. Senior Secondary School Physics by P.N. Okeke and M.W. Anyakoha. And 4. Essential Physics for Senior Secondary School by O.E. Farinde and H.E. Ehime Talo. 5. Calculations in University Physics by Emeka E. Ike. Our contacts are Napoleon Kure 0803636 again 2105. Hassan Buki 08065504346. I take it again. Napoleon Kure 0803636 again 2105. And Hassan Buki 08065504346. Thank you. Till we meet in the next lesson.